All right, this is chapter 19, part 3, and it's on regulation of blood pressure. So, in order to maintain blood pressure, it requires a cooperation of the heart, the blood vessels, and the kidneys. All of this is supervised by the brain. There are three main factors regulating blood pressure: cardiac output, peripheral resistance, and blood volume. And blood pressure is going to vary directly with all three of those things. Ooh, complicated slide. No worries. So if you remember this equation that popped up in the last talk, where blood flow equals blood pressure gradient over peripheral resistance, and we substitute this in for this, and then we rearrange this equation. Trust me, it's the same. What it's going to show us, and you don't have to memorize these equations, okay? Seriously, you do not have to memorize them. But what I do want you to know is that blood pressure is directly proportional to cardiac output and to peripheral resistance. Changes in one variable are quickly compensated by changes in other variables. And then if we continue on, you have to remember that cardiac output equals stroke volume times heart rate. And so what they did was they took the cardiac output out and added stroke volume and heart rate in here to show that anything that increases stroke volume, heart rate, or peripheral resistance will also increase mean arterial pressure. So each one of these variables is affected by something different. Stroke volume is affected by venous return. I'm sorry, not venous return or end diastolic volume. Heart rate is maintained by medullary centers, and peripheral resistance is affected mostly by vessel diameter. Factors can be affected by, so there's two short-term regulations here, neural controls and hormonal controls. We'll spend more time talking about neural controls. And then the long-term regulation are the renal controls. So if we look at this mean arterial pressure, and then in order to increase it, we need to increase cardiac output or increase peripheral resistance. To increase cardiac output, you increase stroke volume and or heart rate. To increase peripheral resistance, you decrease diameter of blood vessels and or increase blood viscosity and or increase blood vessel length. The two main neural mechanisms that control peripheral resistance are one, by just altering blood vessel diameter, which alters resistance. So for example, if blood volume drops, all vessels constrict except those to the heart and brain. And then also the body does alter blood distribution to organs in response to specific demands. Neural controls operate via reflex arcs that involve the cardiovascular center of the medulla, baroreceptors, chemoreceptors, and higher brain centers. So the cardiovascular center is composed of clusters of sympathetic neurons in the medulla. It consists of the cardiac centers, which include the cardioinhibitory and cardioacceleratory centers. There is also the vasomotor center, which sends steady impulses via sympathetic efferents called vasomotor fibers to blood vessels. And what this does is it causes a continuous moderate constriction, which we call vasomotor tone. And then in addition to this other stuff, it also receives inputs from baroreceptors, chemoreceptors, and higher brain centers. Baroreceptor reflexes, so we have located in the carotid sinuses, aortic arch, and walls of large arteries of the neck and thorax. In the event that mean arterial pressure is high, the increase in blood pressure stimulates baroreceptors to increase input to the vasomotor center. This will inhibit the vasomotor and cardioacceleratory centers, which will and it will stimulate the cardioinhibitory center, which will result in a decrease in blood pressure. On the flip side, if mean arterial pressure is low, reflex vasoconstriction is going to be initiated, which is going to increase cardiac output and blood pressure. For example, upon standing, blood pressure falls, and it will trigger the carotid sinus reflex. And these are baroreceptors that monitor blood pressure to ensure enough blood gets to the brain. And the aortic reflex, which is going to maintain blood pressure in the systemic circuit. Now, I do need to point out that baroreceptors are ineffective if the altered blood pressure is sustained. This is high or low. So, for example, they become adapted to hypertension, so they're no longer triggered by elevated blood pressure levels. There are chemoreceptor reflexes. In the aortic arch and large arteries of the neck, they will detect an increase in carbon dioxide or a drop in pH or oxygen. This is going to cause increased blood pressure by signaling cardioacceleratory center to increase cardiac output and signal the vasomotor center to increase vasoconstriction. And then finally, we have the influence of the higher brain centers. Reflexes that regulate blood pressure are found in the medulla. The hypothalamus and cerebral cortex can also modify blood arterial pressure via relays to the medulla. The hypothalamus also increases blood pressure during stress, and it also mediates redistribution of blood during exercise and changes in body temperature. Now, these are things we've talked about before. These are short-term mechanisms that are going to control blood pressure. These are hormonal controls. So we start off with talking about the hormones from the adrenal medulla, and this is epinephrine and norepinephrine. They're going to increase cardiac output and vasoconstriction. Angiotensin 2 is going to stimulate vasoconstriction, and this is going to play a role in the long-term mechanism. ADH, high levels of this can cause vasoconstriction. Again, we're going to talk about this in the long-term mechanism. And then atrial natriuretic peptide decreases blood pressure by antagonizing aldosterone, causing decreased blood volume. And this is a table showing the hormones that I just went over, their effect on blood pressure, the variable affected, and the site of action. The long-term mechanisms, I should say, are renal regulation. And this is because, again, baroreceptors do quickly adapt to chronic high or low blood pressure, so they are ineffective for long-term regulation. And long-term mechanisms to control blood pressure that are in place to control blood pressure are doing so by using the kidneys. And the kidneys regulate arterial blood pressure by two mechanisms, the direct renal mechanism and the indirect renal mechanism. So the direct renal mechanism is literally just how much urine you're producing, right? How much urine a patient or an individual is producing. And the indirect renal mechanism is a renin-angiotensin-aldosterone mechanism. So direct renal mechanism alters blood volume independently of hormones. So an increase in blood pressure or blood volume causes elimination of more urine, which is going to decrease blood pressure. A decrease in blood pressure or blood volume causes kidneys to conserve water and blood pressure rises. So this is what we see here on the left. Decrease in blood pressure, decrease in filtration, decrease in urine, increase in blood volume, increase in mean arterial pressure. The indirect mechanism is a renin-angiotensin-aldosterone mechanism. So a decrease in arterial blood pressure causes the release of renin from the kidneys. Renin enters the blood and catalyzes the conversion of angiotensinogen from the liver to angiotensin 1. ACE, or angiotensin converting enzyme, especially from the lungs, converts angiotensin 1 to angiotensin 2. Angiotensin 2 acts in 4 ways to stabilize blood pressure and extracellular fluid. 1, it stimulates the secretion of aldosterone. 2, it causes ADH to be released from the posterior pituitary. 3, it triggers a person to become thirsty by triggering the hypothalamic thirst center. 4, it acts as a potent vasoconstrictor, directly increasing blood pressure. And that's what we see here on the right. We have a drop in blood pressure. We're just going to start, here. Increase in release of renin. This is going to convert this to this. ACE comes in here and converts angiotensin 1 to angiotensin 2. Angiotensin 2 causes the release of aldosterone, the release of ADH, stimulates the hypothalamic thirst center, and also causes vasoconstriction, all of which eventually increase mean arterial pressure. The goal of blood pressure regulation is to keep blood pressure high enough to provide adequate tissue perfusion, but not so high that blood vessels are damaged. So, for example, if blood pressure is too low to the brain, perfusion is inadequate and the person can lose consciousness. If it's too high, the person can have a stroke. Here are your questions. This is all I have for you for this talk.